Welcome to Amateur Radio's Reflector Magazine by the East Coast Reflector. Volume 26 of the Reflector Magazine, March 2026. Articles featured in this volume: Dick's Corner, The Antenna Farm, EndFed Basics, Heat Sinks Revisited, The Story of Dan and Dick, Basics, Square Waves, Celebrity Callsign W6ZH, Herbert Hoover Jr., World Radio History, Radio Questions Answered. You'll also find information on nets, user-submitted pictures, M1KE, Zoom events, system and connection information, silent keys, and more. Table of Contents. Dick's Corner by WB2JPQ. What's in this article? Dick's Corner. The East Coast Reflector continues to grow, not just in connections, but in the operators who make it work. From representing ECR at Orlando Hamcation to system updates and upcoming events, there's a lot happening across the network. In this article, a thank you to those who represented ECR at Hamcation. Important Echolink connection reminders to keep the system stable. A simple PTT habit that can prevent system timeouts. Details on the upcoming Western New York meet and greet. A reminder about our 15-minute QSO guideline. A call for shack photos for Facebook and the magazine. Improvements in overall system audio quality. Hamcation. The East Coast Reflector was proudly represented at Orlando Hamcation, and we want to extend a sincere thank you to those who helped make happen: K2CMT, KO4FRR, and KE4NTG. Your time and effort are deeply appreciated. Events like Hamcation are a wonderful reminder that our system is more than linked repeaters and nodes. It's people, friendships, and shared enthusiasm for hams. Echolink users. As our system continues to grow, a few important reminders will help keep everything running smoothly. Please use ECR 9050 as your primary Echolink conference server whenever possible. The nodes WB2JPQ, L and WB2JPQ should only be used as backups to ECR 9050. Keeping traffic on the primary conference server helps us manage connections efficiently and maintain stability across the network. We also ask our Echolink users to be especially mindful of their push-to-talk operation. Recently, we've experienced system timeouts due to unintended transmissions. Remember, on a computer the spacebar activates PTT. It's easy to bump accidentally. A quick check before stepping away from your keyboard can prevent unnecessary disruptions and keep the system clear for everyone. Looking ahead, mark your calendars for the Western New York meet and greet on June 20th in Orchard Park, just outside Buffalo, New York. We'll be offering VE testing, and attendees will have the opportunity to operate our special event station on 20 and 40 meters, as well as connect through the ECR system. 15-minute QSO limit Echolink users. As always, please respect our 15-minute QSO guideline when using the system. The East Coast Reflector serves hundreds of users across a wide geographic area. Observing this guideline ensures everyone has an equal opportunity to participate and keeps conversations flowing smoothly. We're also always looking for photos for Facebook and our news magazine. This is a perfect excuse to tidy up the shack, snap a photo, and send it in. We love showcasing the operators who make this system what it is. Finally, thank you to everyone who has been checking and adjusting their audio using the FFT monitor available on the East Coast Reflector website. It's working. Operators are taking pride in their audio quality, and it shows. The overall sound of the system has noticeably improved because of your effort and attention to detail. Thank you for being part of the East Coast Reflector family, for your professionalism, your cooperation, and your continued support of the system. Dick, WB2JPQ.
Meet your control stations. Sometimes people with good intentions act as control operators, but don't represent the ECR. This is the official list of active control stations. Bob, KB3SNM. Dick, WB2JPQ. Kevin, KE7K. Joe, KO4FRR. Kevin, VE3BZ. Vicky, K8VKY. Charles, KC6UFM. Dan, KD2VNU. Backup control stations are also available. Be a quester. QSO Quest is going to be an ongoing initiative designed to encourage increased on-air participation across the East Coast Reflector network. Questers earn points by making QSOs with designated coasters and work toward earning certificates. Any mode may be used. Contact or log through a link on the ECR website, and points are awarded only for contacts made with stations designated by the ECR team. Coming soon. Connecting to ECR is simple, and there is no membership or club to join. Everyone is welcome. There are no fees or permissions. Just connect. If you have audio or connection issues, we're here to help. Simply free. The way that air was meant to be. M1KE instructions for how to connect to the ECR with Brandmeister. The Reflector Magazine is available on YouTube. Watch along on the pages and listen to the voiceover as it reads to you. It's great for blind, visually impaired, people who prefer to listen to the audio, or people who need something to listen to while they mow the lawn. If you know of someone who would benefit, pass it along. The ECR can use your help. We need net controllers and loggers. We also need a Zoom greeter and a podcaster for YouTube. Here's a list of common courtesies for the Reflector. In this article, EndFed Antenna Basics. In Part 39 of the Antenna Farm, Charles KC6 UFM introduces the fundamentals of EndFed wire antennas and how they compare to traditional dipoles. In this article, you'll find what an EndFed wire is and how it differs from a center-fed dipole, the basics of EFHW and long wire antennas, how resonance and harmonics affect multi-band operation, why matching transformers 49-to-1 and 9-to-1 are required, installation considerations, counterpoise needs, and practical trade-offs. This article sets the foundation for understanding EndFed systems before diving into transformer design next time. Hello, ECR family, and welcome to the Antenna Farm. This is your friendly antenna farmer, Charles, KC6UFM. As always with the Antenna Farm topics, I welcome any and all feedback from you, the reader. I'm almost always monitoring the East Coast Reflector, and my email is on my QRZ page. I am also on the ECR for almost every Tuesday night TechNet, so this would be a great place to ask questions, too. Feel free to reach out to me with any comments or questions. But there's a new, and in my opinion, great place to ask questions about the antenna farm or antenna systems in general. Join me, along with other Elmers, in the East Coast Reflector Zoom room on the first and third Thursdays of each month at 8 p.m. Eastern for the Ask an Elmer/Be an Elmer event. This is a chance for all hams, especially those new to the hobby, to ask questions that may be too involved to get detailed answers from the TechNet. I look forward to you joining us and asking your questions. Today at the Antenna Farm, we're starting a loose series of articles getting into the nitty-gritty of EndFed wire antennas. In this installment, we'll start off taking a look at a few definitions, so we're all on the same page with the terminology and the basics. EndFed antenna types. EndFed half waves, EFHW. This is a bit of a misnomer. An EFHW is only a half wave long at its lowest design frequency, usually called the primary frequency. At higher frequencies, the antenna uses harmonics of the primary frequencies. A center-fed dipole, a total of a half wavelength long, will show resonance at the primary frequency as well as on even harmonics. So if we have a dipole cut to resonate at 80 meters, say 3.25 megahertz, it will also show resonance at 6.5 megahertz, 13 megahertz, 19.5 megahertz, 26 megahertz, and 32.5 megahertz. Some of these numbers are close to a few of the other HF bands. The bottom line is that by careful selection of the primary frequency and using an antenna matching network, aka an antenna tuner, you can cover a good number of bands with this system, but very rarely more than 4 bands. An EndFed antenna, however, will be resonant at its primary frequency and on both even and odd harmonics. If we use the 3.25 megahertz primary as we did above, the wire will also be resonant at 6.5 megahertz, 9.75 megahertz, 13 megahertz, 16.25 megahertz, 19.5 megahertz, 22.75 megahertz, 26 megahertz, and 29.5 megahertz. Many more of these sample resonate points are generally much closer to the several ham bands. Again, by careful selection of the primary frequency and using a matching network, it is fairly easy to have an antenna that will load well on most of the HF bands. Long wire antennas. Looking at the above discussion of EFHW antennas should make clear their inherent fault. In order to match as many bands as possible, the primary frequency needs to be as low as possible, and that can lead to some very long antenna wires. In our example of an 80-meter band primary, the antenna would need to be on the order of 155 feet long. While many hams could get this much wire in the air, it does not need to be in a straight line or all at the same elevation. It's still a bunch of wire. Luckily, the long wire antenna provides a solution. A common point of confusion with long wire antennas is that they are sometimes called incorrectly random wire antennas. This name is incorrect because the wire length needed is anything but random. The wire must be a very specific length determined by the desired band operation. The more bands you wish to operate on, the more specific the length becomes, and the fewer usable lengths you will have to pick from. The secret of the long wire antenna is that it is not resonant on any of the bands you wish to use. That's right. The EFHW dipoles and many other antennas you may be familiar with are resonant, but the long wire antenna is a non-resonate system. Continued on page 84.
Connections. Connections printable. There are many ways to connect to ECR. For a printable list, go to ecr.radio/connect. There, you will find the information on the many different ways to connect. Got DMR? Connect to the East Coast Reflector using 3215714. You can find a map of repeaters on eastcoastreflector.com. If you have a repeater that's connected at least 60% of the time, is 10 watts or more, has an outside antenna, and is open for others to connect, then let us know and get on our map. Social media. The ECR is building up its social media presence. Join our Facebook group so you can enjoy our ham radio content and stay up to date on ECR information, and so you can update us on your ham shack and ask questions. Just like on the air, we don't tolerate trolls. You're free to ask questions troll-free. We keep it an enjoyable place. Check us out also on X, Twitter, Groups.io, YouTube, and most recently Discord. We look forward to you joining us. System diagram of how the ECR is linked together. What's in this article? Basic heat sink calculations. Harry ESM 0 VPO. This article is a practical, experience-driven look at where heat really comes from, why it destroys otherwise good designs, and how to deal with it before the magic smoke escapes. In this article, you'll explore why heat is often the real limiting factor in power electronics, how thermal runaway happens, even in low-power circuits, what degrees Celsius divided by Watts ratings actually mean in the real world, how to calculate heatsink size instead of guessing, why power supplies are especially brutal heat generators, practical methods for making, evaluating, and reusing heatsinks, common mounting mistakes that sabotage cooling performance. Based on decades of hands-on experimentation, this piece bridges the gap between theory and bench reality, helping you design projects that survive continuous use, not just initial testing. This page is an update to my original heatsinks page, but now there is a lot more detailed explanation. I hope that you can get something from it. Introduction. My interests in radio and electronics extend from digital, analog, radio frequencies, audio frequencies, small signal, and even projects using high powers. Over the years, I have pursued these interests, but always relied on high-power equipment to power my projects, or even design high-power equipment. Power projects often generate a lot of heat, which must be conducted away from the device generating it. Constructors often consider heat as an unavoidable nuisance and do not actually take much trouble in the design to get rid of the heat. This heat can cause the best of designs to fail when a project is put into service. It is quite common to simply guess at the size of heatsink, get a heatsink that will fit somewhere convenient, then build. I used to be that way myself, but in the late 70s I began using power transistors and the tears began. I had to educate myself. I could not find any mathematical formulas to guide me with heat distribution, power, and temperature. So I did loads of experiments, and I developed my own formulas for estimating the size of a heatsink needed to keep a project cool. This article is based on my notes from those experiments, and I hope that sharing with you the results can help you improve your project building and prevent a catastrophic failure due to lack of care with heat distribution and temperature. Power and heat. All devices that dissipate power, such as transistors, integrated circuits, resistors, dummy loads, etc., should not normally be allowed to become much hotter than about 100 degrees Celsius. Most silicon transistors will happily operate hotter, but do not count on it. Most semiconductors, especially germanium transistors, can change their electrical properties when they get hot. Integrated circuits and transistors drawing current may start to draw even more current due to heat, and the increased power dissipation causes even more current to flow. This evil circle is referred to as thermal runaway. Thermal runaway can occur in high-power circuits where you expect high powers, but even a small RF transistor amplifier delivering, say 50 milliwatts of power, can have a small metal case that cannot get rid of the small amount of heat. Just 100 milliwatts, 0.1 watts, of total power can seriously kill a small signal transistor when the power causes the temperature to rise beyond the capability of the device. 218 metal encapsulated transistor, 2N2369A. Project boxes and equipment cases can also contain heat, preventing it from being dissipated elsewhere. A heatsink on a device will get heat away from the device and protect it, but if the project box has no ventilation or thermal conductivity, then the internal temperature will rise. Your project may work for a few hours continuously, but when the temperature reaches a critical level, something will give way. Plastic project boxes can contain heat equals temperature rise. Let us take the case of the Simple Power Supply Unit, PSU, described elsewhere on my home pages. The PSU may deliver 3 amperes at up to 15 volts at the output. The internal power for the PSU printed circuit board, PCB, may be 20 volts. The basic formula to calculate power is W equals A x V, watts equals volts x amperes. If you use the PSU to supply a project with 15 volts at 3 amperes, then the project is therefore dissipating 3A x 15V equals 45 watts. That is actually a lot of heat for an electronic project. Continued on page 91.
Join us Tuesday nights at 8 p.m. Eastern for the ECR TechNet. And the infamous Morning Brew weekdays from 7 to 9 a.m. Be a net controller on our Open Mic Net Wednesdays at 8 p.m. Register at ecr.radio/join open mic. The Youth Net is run from the East Coast Reflector Zoom room with the support of the ECR team. All kids and their parents are welcome to come in at 7 p.m. Eastern Standard Time, an hour before the net, to hang out and get to know each other and see how the net runs. Third-party check-ins and net controllers are encouraged. Adults are welcome to check in. Kids are welcome to check in with each net controller. Last month's net questions. Join the 20-meter net on Thursdays at 10 a.m. on 14.317, and the 40-meter net on Saturday mornings at 9 on 7.245. Caption this. Write a funny caption for this photo. A panel of our elite judges will decide on the best response, and the winner will be announced in the next issue. Play along on the Trivia Net Saturday nights at 11 p.m. Dick and Dan. A story of how Dan first met Dick WB2JPQ in 1984 as a 16-year-old new ham, and how Dick's patience, mentorship, and friendship helped guide him through his early radio adventures and shaped the person he became. I first met Dick WB2JPQ in the summer of 1984. I was all of 16 years old with a still fresh call sign of KA2TSV, and had recently gotten a UHF handheld, which I had borrowed the money from my grandfather to purchase. There were very few UHF repeaters or users on the air at that time, and it took a few weeks to finally make a handful of contacts. I met him on the 444.10 repeater that was on top of what used to be Marine Plaza, and still is the tallest building in Western New York. He was probably my second or third contact on UHF. With our mutual interest in Motorola and commercial radios, we quickly became friends. That same patience that he shows today with our young enthusiastic operators has always been his style. At the time, I didn't think of myself as some young obnoxious Motorola fanboy who wanted to work in radio, but looking back, I'm amazed at his patience and encouragement. Some others would have just rolled their eyes and brushed me off. Because of this, I remember to treat young hams with the kindness that he had shown to me, because not everyone was that kind. Dick has been more than just a friend, he was also a mentor. He taught me so many tricks of the trade while assisting him with his repeaters up on top of various cool locations in and around Western New York. We have had countless trips to sites where we were highly successful because of excellent planning. Some trips were successful because, between the two of us, we figured out how to make do with random parts lying about in the trunk. Sometimes success was just plain old blind luck. And on occasion, we left scratching our heads, wondering just what went wrong. And some moments live on in hilarious memories. The 50-ohm splint. 10 dB stick. Dick being covered head to toe in mud, with the only clean spot on him being around his eyes, where he took off his mud-covered glasses so he could see. As much as my parents, Dick's kindness, friendship, and mentorship have truly helped shape who I am today. He was always around and encouraging for me getting my first job in two-way radio at Metro Electronics. I feel like he was as excited for me as I was. He was a frequent visitor and friend to all at my second radio job and 10-year run at LJ Raymart. We spent many an afternoon, and after hours, goofing around with repeater projects in the shop. We also spent probably too much time blowing assorted scrap electronic things up, intentionally, as the company owner walked through, giving us both that raised eye look, before shaking his head and walking away. I have known Dick so long that he is basically an adopted family member. He's one of the few people in my life that I've known longer than my wife, who also considers him a close personal friend. Though my life has taken me away from Western New York, and our in-person visits are only a few a year, I still consider him my closest personal friend. I look forward to every time we get to sit down and chat, even if it's only for a few minutes, as we head back to Michigan. Without Dick's friendship, I would not be quite the person I am today, both from a personal and professional perspective. And for that, I am eternally grateful. Date in 2025. N2BH, WB2JPQ, W2PUT, WB8ODF, Corey, KB0P.
The East Coast Reflector Volunteer Diagram. Audio check. There are great audio tools on the website at eastcoastreflector.com. There's a Listen Live player for listening anytime, equipped with a visual audio meter. There's a second player with a 2.5-minute delay. This allows you to do your own audio check. To hear what your audio sounds like, load up Listen Live on the website. Pick up your radio. Give your call sign and say this is an audio test. No response necessary. Then wait a minute and listen to the playback. Still stumped? Come into our Zoom room for advice at bit.ly/ECR daily. The ECR Helpline. If you're having a difficult time connecting to the ECR or need to make us aware of a problem, call or text our helpline at 746-427-4142. We'll help you the best we can. This is not for bad audio or rude hams. This is for things that need current attention, like someone sleeping on the mic about to time out the system or someone being very aggressive. We appreciate your help. Did you know that we have a gift shop? You can help to support the East Coast Reflector at the gift shop. You can get your call sign put on an ECR shirt starting at $17.68, coffee mug from $12.60, or a polo from $22.49. Be a contributor. Do you want to help contribute to the magazine? Send in your article, project, story, comment, and suggestions to editorecr@gmail.com. You don't have to be a good writer if you have a good story. Everything will be polished and sent to you before it's published. You should know. The East Coast Reflector and its Reflector Magazine is all volunteer run. We charge nothing to use the system and nothing to subscribe to the magazine. The system has hundreds of nodes and repeaters connected at any given time. We incur a lot of expenses to maintain such a large system. If you use the system or enjoy the magazine, please consider helping by contributing to the system by going to eastcoastreflector.com and click on Donate. Your contribution is greatly appreciated. What's in this article? The Basics. Square Waves. By Vicky Gaby. Square waves are everywhere in modern radio gear, even if we don't hear them directly on the air. They power timing circuits, digital systems, and keying, and they explain a lot about harmonics and clean signals. In this article, you'll discover what a square wave actually is in plain language, how square waves appear in CW, digital modes, and microcontrollers, why sharp edges create harmonics, how filtering shapes signals and reduces interference, why understanding square waves makes you a better operator. Once you understand what's happening behind the scenes, a lot of radio technology starts to make much more sense. Square waves. If you've spent any time around ham radio, you've already run into square waves, whether you knew it or not. When you tap a Morse key, send a digital mode, or play with an Arduino or Raspberry Pi project, a square wave is usually working behind the scenes. They may sound technical, but the idea is actually very simple. A square wave is just a signal that turns on and off very quickly. The easiest way to picture it is to imagine flipping a light switch up and down over and over. When the switch is up, the light is fully on. When the switch is down, the light is fully off. There's no dimming or fading, just instant changes. If you looked at that on a screen, it would look like flat tops and bottoms with sharp edges, kind of like a row of little squares. That's where the name comes from. Hams have square waves all over their shacks. When you send CW, the transmitter turns on and off rapidly as you key the signal. Inside most radios, computers, and power supplies, tiny circuits switch on and off thousands or millions of times per second. Microcontrollers that run homebrew projects use square waves as timing signals, telling different parts when to do their jobs. Even though your transmitted signal might look like a smooth sine wave on the air, there are usually square waves inside the radio helping make that happen. One important thing to know is that square waves can create trouble. Because they switch so suddenly, they don't just make one frequency. Those sharp edges produce extra copies of the signal at higher frequencies. These are called harmonics. For example, if you had a perfect 1 MHz square wave, it would also create signals at 3 MHz, 5 MHz, 7 MHz, and so on. Without control, those extra signals can leak out and interfere with other bands, which nobody wants. That's why radios use filters. Filters smooth out the harsh edges of a square wave and help remove the unwanted extra frequencies. When a CW signal sounds clean without key clicks or splatter, it's usually because the radio is shaping and filtering the square like switching inside. Cheap or poorly designed equipment may not filter well, which is why some signals sound messy or seem to pop up in places they shouldn't. Even with all this potential for interference, square waves are incredibly useful. They're easy to generate, reliable, and perfect for timing and digital control. Modern radios and accessories depend heavily on them, especially anything involving digital electronics. So the big idea is this: a square wave is simply a fast on-off signal. It's everywhere in modern radio gear. It can cause interference if not filtered, but when handled properly, it's a powerful and essential tool. Understanding square waves helps you appreciate what's going on inside your equipment and why clean signals don't just happen by accident. They're carefully shaped and controlled. Once you grasp that, a lot of radio technology starts to make more sense.
Net questions. Here's a list of most of our net questions. Ever wonder how your answer compares or what the results were? Click the question to see the results. There's questions from the Morning Brew, and the TechNet, and the TriviaNet. The ECR has unique log sheets, and you're welcome to watch along. You can see where you're on the log, answers to the questions, and even birthdays and more. Go to ecr.radio/logs to get access to view all of the net logs. Text or email to get your spot on the log. Our nets can be so busy that people have a difficult time getting in. We want to help everyone get on the air, so we came up with a unique way to get more people on the air. Text your call sign to 716-317-9050. Standard messaging rates apply. You can also email your call sign to text@ecr.radio. This will get you onto the log. This is not for ins and outs. It's to help get people on the air and through the pileups. Our nets. Celebrity Call Sign by Joe KD2TFB. Herbert Hoover Jr. W6CH. Herb was born on August 4th, 1903 in London, England, the first son of Herb and Lou. He was a victim of the 1918 flu epidemic, which caused him to have impaired hearing for the rest of his life. But Herb also had an interest in electronics, So he made himself a hearing aid. He traveled a lot as kid, but the family eventually settled near Stanford University. He took great pride in serving as water boy for the Stanford Indians football team. Herb would go on to attend Stanford, just like his father, and earned a general engineering degree in 1925. He later studied at the Harvard Business School and was awarded a Master of Business Administration with distinction before winning a fellowship from the Daniel Guggenheim Fund to study aviation economics. His work focused on the economics of radio in the aviation sector. In 1928, Herb was hired by Western Air Express to set up its communication system. Over the next year and a half, he set up a network of stations across the western United States capable of guiding radio-equipped aircraft. He did not stay at Western Air Express, however. You see, it's possible to use radio to help prospect for oil. He founded United Geophysical in 1935, and by 1939, he had 200 employees working in 5 labs, perfecting the art of exploring for oil by using seismology. In 1937, he founded a related company, Consolidated Engineering Corporation, which focused on instrument manufacturing. Eventually, Herb earned the position of Undersecretary of State, where he served from 1954 to 1957. He was such an amateur radio enthusiast. In 1962, he was elected president of the IRL. This celebrity call sign is W6EH, having once belonged to Herbert Charles Hoover, son of the 31st United States. President Herbert Clark Hoover, but more widely known as Herbert Hoover, Jr. He suffered a sudden stroke on July 6, 1969, and became a silent key 3 days later at Huntington Memorial Hospital in Pasadena, California. Celebrity Call Sign Archive. QSL Cards courtesy of hamgallery.com.
Hamcation 2026 Pictures. With a special thanks to Mike, K2CMT, and Joe K04FRR for organizing, setting up, and representing, and for Walt KE4NEG for sponsoring our table. Radio Questions Answered by A.P. Peck, The Experimenter's Library No. 3, 3D reprint, February 1924. For entertainment purposes only. Use common sense. This is from 1924 and outdated. The original article is very long. Parts of the article will be split up into 7 pieces over the next issues. The full original article can be found at worldradiohistory.com in the Experimenter's Library No. 3, Part 4 of 6. Why are an aerial and ground used? Question number 25. What is an aerial? Answer. An aerial is any form of conductor which is used to pick up radio waves. It may consist of a single wire as shown in the illustration. This is a splendid receiving aerial, especially when a crystal set or only a single tube is being used. Another type which is very good when an inside aerial is required is that consisting of a wire running around the molding of a room. It is preferable to use insulated wire for this purpose, although it is not absolutely necessary. When 1 or 2 stages of radio frequency amplification, such as will be explained later, are used, a loop antenna on the order shown may be employed. Either the spiral or solenoid type will give good results, and in size need not be larger than 2 feet square. Even smaller sizes will give good results. When using an outdoor antenna, it should always be very well insulated from all surrounding objects and should have insulators at each end. It should not pass through the branches of trees and should never be brought close to telephone, electric light, or high-tension lines. The wire used should preferably consist of stranded phosphor-bronze, although solid copper wire will give good results. The size should be no smaller than number 14 gauge, and where the aerial is subject to severe weather conditions, number 12 gauge should preferably be used. Question number 26. Why is a ground used? Answer. Every electrical circuit, in order to operate efficiently, must make a complete circuit. That is, it must have one way of getting to a place and one way of returning. In radio, the ether is used for one path and the energy returns to the ground. Therefore, it is quite essential that a good ground connection be made in order to oppose as little resistance as possible to the flow of the current. A ground connection fastened to a water, Steam radiator or drain pipe with ground clamp will give good results. If it is impossible to make a connection to any of these pipes, a length of iron pipe about 1 inch in diameter by 7 feet long driven in the ground, or metallic bodies, such as illustrated, will serve as excellent grounds. In any case, they should, if possible, be placed in a moist part of the earth. Question number 27. How should a lightning switch be installed? Answer. The diagram shows the method of mounting a lightning switch. It should be placed on the outside of the house, and the lead brought in through an insulator to the set. A separate outside ground should preferably be used for a lightning protection, although the Board of Fire underwriters now permit the use of an inside lightning ground. If desired, the same ground may be used both as a lightning ground and also for the ground used in connection with the set. Question number 28. How should a lightning arrestor be connected? Answer. The connections for lightning arrestor are given in the accompanying diagram. Only such a type of arrestor as is approved by the Board of Fire underwriters should be used. A lightning arrestor usually consists of 2 pointed rods enclosed in a glass bulb from which all the air has been exhausted. It may take on other forms, however, and may consist of 2 plates placed edge to edge and about 1/16 of an inch apart. Various types are made by different manufacturers. However, the purpose of all of them is the same. They are designed to form a pathway for any abnormal charges of electricity which may accumulate on the aerial during a thunderstorm, and allow these charges to pass the ground without injuring the receiving instruments or entering the house where they might cause damage. Question number 29. Are both a lightning switch and an arrestor necessary? Answer. Both are not required, but it is a very good idea to use both. In such a case, you have double protection from lightning, and even if you do forget to close the switch when through using the set, the protective gap or arrestor will provide sufficient protection. They should be connected up as shown in the diagram. Question number 30. Is there any advantage in having 2, 3, or 4 wires in the aerial? Answer. In transmission, it is desirable to have a multi-wire aerial, but for reception it will be found that a single wire will give almost as good results. In fact, the installation of a multi-wire aerial would make very little noticeable difference in signal strength. Taken all in all, it is hardly worth the expense and trouble to erect a multi-wire antenna for reception purposes. Question number 31. What is a counterpoise and when should it be used? Answer. As stated under question 25, it is necessary for every electrical current to have a return circuit. This can be furnished by means of what is known as a counterpoise, and which may consist of an arrangement similar to the aerial, but suspended only a few feet above the ground. This is used where only a poor ground connection can be had and provides a necessary surface so that it may act, together with the ground, as a condenser. Continues in volume 26 with the how and why of vacuum tubes question. What is a vacuum tube? Why is a vacuum tube evacuated? How does a vacuum tube operate? What is a soft tube and what is it adapted for? What is a hard tube and what the best use? All of the ECR nets and events are on our calendar at eastcoastreflector.com. Subscribe to the calendar to stay up to date. Ask an Elmer Zoom meeting. Everyone is welcome to come in and ask questions or help answer questions the first and third Thursday of each month. On the second Thursday of each month is our ECR virtual town hall meeting. Stop by to ask questions, make suggestions, and learn about the system. Operator Oddities. Text from my daughter. I think it's time to stop with the radio for tonight. My rope lights are flashing, and it started to look like a horror movie in my bedroom. From my son. How are you coming through only one of my earbuds? And why are you yelling about Yankees? Radio crossword. All of the answers can be found in this issue of the magazine. Ham Comics. Try a quick little general exam practice. A handful of questions to keep your skills sharp or to help practice to take the test. Birthday call sign word search puzzle. You can add your birthday by going to ecr.radio/birthday. And of course a jigsaw puzzle. You choose a number of pieces and put it together from your device. Continued from page 19. Generally speaking, the longer the wire is, the better it will work within the limits set by the desired number of bands. In other words, if the calculations show that you could use either a 60-foot wire or a 110-foot wire, the 110-foot length is the better choice if you have room. The calculations to determine usable lengths are not hard, just simple multiplication and division. The calculations are, however, quite tedious because you need to make sure that a given length is not resonate on any of the desired bands of operation. This leads to a situation where you pick a frequency range, do the calculations to get the lengths, and then compare that to the lengths for all the other bands you want to operate on. Lots of number crunching, and the potential for errors is high. Could there be a better job for a computer? Go to Google and do a search for EndFed.py, and you'll find a Python 3 script that will do these calculations for you. Windows and all flavors of Linux have support for Python 3. I can't personally say that iOS on Apple machines do or not, but I can't picture Apple leaving something like that out. The documentation of the script is built into the script itself. So if you open EndFed.py in a text editor or viewer, you will see the command structure. To use EndFed.py, simply enter a terminal and type Python 3 EndFed.py for ABC, where ABC are the bands you're interested in. It is strongly suggested that you use the F option to look for conflicts at the full wavelengths as well as the half wave points. I have modified the original EndFed.py to include the 160M, 80M, 60M, 40M, 30M, 20M, 17M, 15M, 12M, 10M, 6M, 2M, and 1.25M bands. You can download the modified script here. In the modified script, valid bands are 160, 80, 60, 40, 30, 20, 17, 12, 10, 6, 2, 1. Separate each band value with space. Note that 1 is for the 1.25M band. Depending on your Python 3 installation, you may need to add the matplotlib package. See your distribution documents for how to do this. EndFed.py will give you a nice graph of usable lengths based on your desired bands. Again, longer is better, but the shorter lengths will work, just not as efficiently as the longer wires. Pick the longest wire length you can. Again, remember that the more bands you want to cover, the fewer choices you will have for lengths that will cover them all. This effect is particularly pronounced as you add the higher frequency bands. This brings us to the major drawback to long wire antennas. You will need an antenna matcher to make this thing work. Odds are the built-in antenna tuner in many radios will not work, and you'll need an external system. Ideally, a matcher with a roller inductor and nice, big air variable capacitors should be used as it will easily match a long wire. With that said, my LDG at 600 pro II has no problems matching my 108-foot long wire on 80 meter to 6 meter, but it does take a little time to find a match at 160M. The big benefit to a long wire is that it can be much shorter than an EFHW, and it can cover all the ham bands at the same time. Benefits of EndFed wire antennas. For the purpose of this comparison, we'll be looking at an EndFed versus a traditional center-fed dipole in the 160 meter to 6 meter ends, a total of 11 bands. Wide band coverage. Dipoles can, with proper design and consideration, cover as many as 3 bands. In a few rare cases, you can get 4 bands. In most cases, a simple matching unit, like the one built into your radio, will suffice. EndFed antennas can quite easily cover all 11 bands. In many cases, the built-in antenna tuner in your radio will do the job with an EFHW. If you elect for a long wire design, you will need a capable external matching system. Ease of installation. Dipoles require supports at both ends of the antenna and some way to get the feed line to the center point of the element, often meaning that you will need 3 supports. The mechanical complexity of providing proper support and access can be a challenge. Dipoles do not need any counterpoise or radials. EndFeds need only 2 supports, one at each end, since the antenna is fed at the end. The simple solution is to attach the feed point to the wall outside of your shack. This gives you one mounting point and reduces the length of your feed line to the antenna. The other end support is all you need worry about. EndFeds need a counterpoise. In some cases, you can use a shield of the coax to perform this duty, but this is not an optimal solution. A better way to go is to have one or more wires act as the counterpoise. The best way to do this is to bury the counterpoise wires about 3 inches below grade. This protects the wires from mowing and other damage, and more importantly, eliminates the need for a tuned counterpoise. The wires can be of any length, although longer is better. While one wire will get the job done, more or less, more wires are better. The perfect counterpoise for an EndFed is to mount the feed point on a pole driven into the ground, about 6 inches above grade, not more than 12, and then run as many counterpoise wires as you can, spaced as far apart as possible. The wires should be at least 10 foot long and buried between 3 and 6 inches deep. Going with more than 16 counterpoise wires will show little, if any, observable difference compared to just 4 wires. Costs. At the end of the day, there is very little cost benefit of either antenna over the other. In the strictest terms, a simple dipole may be a few dollars cheaper than an EndFed. Maybe. Ease of construction. If you're planning to build one of these antennas, there is one major thing to keep in mind. A dipole is as simple as it gets. All you need is 2 pieces of wire, each a quarter wavelength long, and 3 insulators, one each at the ends and center. That's it. An EndFed needs just 1 piece of wire a half wavelength long, 2 insulators with 1 at each end, and a matching transformer. This is where the rub lies. An EFHW will have a feed point impedance of about 2,450 ohms, so you need a 49-to-1 matching transformer. A long wire has a feed point impedance of around 450 ohms, so a 9-to-1 transformer is needed. You can build, fairly easy to do, or buy a matching transformer. Prices to buy are in the $100 range, but the same transformer can be built for around $30 in a couple of hours' time. All things being equal, it is easier and faster to build a dipole rather than an EndFed. These are just the basics, an introduction, if you will, to the use of EndFed antennas in ham radio. Next time on the Antenna Farm, we're going to look at the design of the needed impedance matching transformers for EndFed antennas. If you know of an antenna construction article on the web, please drop me a note with the pertinent information, and I will look at it for consideration as an article for the Antenna Farm. Take care in 73. Charles, KC6UFM. Previous articles by Charles, KC6UFM.
Continued from page 28. But what is happening inside the power unit? With a pre-regulated voltage of 20 volts, the regulator transistor has the remaining 5 volts across it, also at 3 amperes. The transistor is therefore burning 5 volts times 3 amps equals 15 watts into heat. If you now turn the output voltage of the PSU down to 1 volt, then the load will dissipate 1 volt times 3 amps equals 3 watts. But the dissipation inside the PSU gets much worse. The series regulator transistor now has 20 volts, 1 volt equals 19 volts between collector and emitter. It is also conducting 3 amperes, so it is dissipating 19 volts times 3 amps equals 57 watts as heat. What do we do with all this heat? Use a heatsink, of course, but how big does that heatsink need to be? Heatsink characteristics. Heatsinks are given a characteristic specification in degrees per watt, usually degrees Celsius, degree C/watt. ATO5 transistor, for example, without a heatsink has a case heatsink characteristic of somewhere in the region of 220 degrees Celsius per watt. So for every watt you make it dissipate, it will increase its temperature by 220 degrees Celsius, or about 240 to 250 degrees Celsius at normal room temperatures. That's hot enough to melt solder. We obviously need more metal to soak up and radiate away the heat in order to keep the temperature down. Heatsinks can come in a wide variety of forms, shapes, and sizes. A small transistor dissipating 3 watts of power with a 25 degrees Celsius per watt specification heatsink will be cooled to 3 watts times 25 degrees Celsius plus room temperature, 20 degrees Celsius maybe, equals 95 degrees Celsius. With a small heatsink, the transistor will therefore survive. The regulator transistor in our 15-volt power unit will not survive. The heatsink simply conducts heat away from the device and dissipates it into the room, so the larger the surface area, the lower, better, the degree C per watt rating of the heatsink. So how big must the heatsink be? Big and small heat sinks, left is fan assisted, right is convection air cooled. Size of heatsink. Our transistor in a 15 volt at 3 amperes PSU will dissipate a maximum power of 60 watts if the output leads are short-circuited, worst case, and it will happen sooner or later. So to keep the temperature below 100 degrees Celsius, we should calculate the smallest heatsink required. The room temperature is assumed to be 20 degrees Celsius, so the transistor can increase its temperature by 100 degrees Celsius minus room temperature equals 80 degrees Celsius. 80 degrees Celsius divided by 60 watts equals 1.333 degrees Celsius per watt. So you cannot just pick any old heatsink from the junk box or order one from Etsy, an international platform with many sellers based in China. If you work out the heatsink specification in degree C per watt 333 in the above example, then enter this in this table and click Show Area to find the heatsink surface area needed. This is only a potentiometer connected to a perfect power transistor base with a current gain of almost infinity, greater than 1 million. The base emitter voltage drop is 0 volts. As the potentiometer is varied, so the output voltage varies from 0 volts to 30 volts, but the transistor has 535 volts across it. So how much power will the transistor dissipate as heat? Let us calculate a few random examples and put them in a table. As you can see, the power dissipation demand has a tendency to increase as the PSU output voltage decreases. A simple PSU for 0 to 35 volts at 0 to 3 amperes can be continuously put to use for hours, days, weeks, months, or even years with any of the above applications. Charging the 24-volt Lorry battery is much less demanding than charging lower voltage batteries, even less than charging a single an IMH cell for my model boat. The lower the output voltage, so the higher is the voltage drop across TR1. The heatsink is therefore, perhaps, the most important component in a PSU. So let us look more closely at heatsink construction. Making heatsinks. You can evaluate homemade heatsinks by using the following formula. As an example, let us make a heatsink with about 1 mm 20 SWG, thick aluminum sheet, copper will be best, folded as shown, viewed from above. Typical heatsink construction. The heatsink is going to be 20 centimeters wide, W, 10 centimeters deep, D, and 12 centimeters high, not shown viewed from above. Each fin is 10 centimeters times 12 centimeters equals 120 centimeters. Each fin also has two sides. Area equals 240 square centimeter. There are 10 fins, so we have a total of 2,400 square centimeter. The rear plate has also two sides times 20 centimeters times 12 centimeters equals 480 square centimeter. Total area equals 480 plus 2,400 is equal to 2,880 square centimeter. Since n the square root of 2,880 is equal to 53.66, we therefore have 50 divided 53.66 equals 0.932 degrees Celsius per watt. That would be an expensive heatsink to buy. It may not look pretty homemade, but it works just as well. Use existing heat sinks. It is common practice to use the chassis of a unit as the heat sink, or part of it, but this is limited to a single panel, and steel cabinets are not very good conductors of heat. In addition, the power transistor must be electrically isolated from the metal, which also impairs the heat transfer from the transistor to the heatsink. An aluminum box 5 centimeters times 10 centimeters times 20 centimeters would therefore have an outside surface area of 5 times 10 times 20 is equal to 1000 cm superscript 2. Square root of 1000 is equal to 31.623, so our equipment case has a thermal dissipation of 50 divided by 31.623 degrees C per watt equals 1.58 degrees Celsius per watt since we need one. 13 degrees Celsius per watt we do not have enough, but we can use the case as a part of the heatsink and cut down the size of the heatsink we need. Notice that the inside of the case was not taken into account. The case is a closed box, so without ventilation, the inside of the case will dissipate nothing. Convection-cooled heat sinks must be mounted so that the fins or vanes are vertical, because warmed air rises. If you mount the heat sink with the vanes horizontal, then there will be little airflow between the vanes and the heat sink will not perform as expected. How big do we need it? Let us work backwards using our 15-volt PSU regulator transistor that is still dissipating over 60 watts without a heatsink. Let us mount it in the 5 centimeters times 10 centimeters times 20 centimeters cabinet we found above. Transposing the formula we have, We know we need a heatsink of 1.13 degrees Celsius per watt, so putting this into the formula, we get 1957.9 square cm of heatsink required. We already have 1,000 in the case, so we must provide the other 960 square centimeters as vanes, or fins, on the back of the box. 10 fins of 96 square cm, 48 per side, will do the job. Each fin can therefore be 5 centimeters times 10 centimeters. Forget the backplane, that is part of the case. 5 centimeters times 10 centimeters is still quite big, but the case is only 5 centimeters deep, so it is reasonable. Including heatsink, the case will now be 5 centimeters times 20 centimeters times 20 centimeters. Note that only the fins were considered. In reality, a 5 centimeters tall case would be a little small, so the case would not be able to accommodate the mains transformer, even if you used three 6.3 volt 3 amp filament transformers. Increasing the height of the case by 1 centimeter would reduce the size of the fins by 2 centimeters, 6 centimeters times 8 centimeters, as opposed to 5 centimeters times 10 centimeters earlier. Evaluating heat sinks. Imagine you have just bought a pack of 4 heat sinks from Temu.com, and there is no thermal specification given. The same is true for all heat sinks sold on Temu, Etsy, Banggood, Wish.com, and Frugo. Perhaps you have found a heat sink in your junk box. How can you find out how many degrees temperature rise you will get for 1 watt of power? The solution is quite simple. Physically measure it and calculate the total exposed surface area and calculate it. The formula is, note the decimal delimiter can be either a period or a comma. For example, entering 12,123.45 will be interpreted as 12.12345. Worked example. My heatsink was bought from Temu. Common cost me 14 Swedish kronor, GB pound 1.00, or $1.34. No specification data was given other than it is 40 millimeters times 20 millimeters. Really helpful not. When I measured the heatsink, it was 4 centimeters times 4 centimeters times 2 centimeters. Each exposed fin area is 4 centimeters times 1.7 centimeters, 40 millimeters times 17 millimeters. So there are 11 fins with 22 radiating surfaces. The two end surfaces are 4 centimeters times 2 centimeters equals 8 square centimeters, but the other 20 are each 6.8 square centimeters. So the total surface area is 20 times 6.8 plus 2 times 8 equals 152 square centimeters. Entering 152 into the formula above, we get 4.0555 degrees Celsius per watt. So now we know that for only 80 degrees Celsius increase from room temperature, 20 degrees Celsius, we will reach a temperature of 100 degrees Celsius with only 20 watts of power. Note that 100 degrees Celsius is higher than the threshold of pain, so if the heatsink is to be mounted on an equipment case, then it should be a metal case and the fins mounted vertically. If bolted this heatsink to the outside rear of my little plastic equipment case, I can only tolerate 50 degrees Celsius maximum, 20 degrees Celsius room temperature, plus 30 degrees Celsius rise in temperature, which limits my little 35-volt bench PSU to just 7.5 watts, or 200 milliamperes maximum output current, worst case. Okay, I can mount the heatsink on PTFE standoffs from the plastic, use 2 heat sinks, and add a fan. Then I can get 1 ampere if the fan is powerful enough. Mounting devices. Almost all devices that we need to mount on a heatsink have a metallic surface from which the heat is to be conducted. This surface is usually electrically connected to one of the terminals of the device. We therefore need to place an electrical insulator between the device and the heatsink. In the case of transistors, this is in the form of a mica washer or disc. The disc is lubricated with a heat-conductive oil to help the heat to be transferred. The oil and the washer should never be omitted if the device is to be effectively protected. Insulation and washers for mounting TO220 transistors. Since aluminium is not the world's best conductor of heat, I often lay a strip of copper the full length of a heatsink to distribute heat evenly along the complete length of the heatsink. The device is mounted on the copper, and the copper distributes the heat to the rest of the heatsink. This avoids a local hotspot where the transistor is thermally connected. One small suggestion here. Look at your local computer shop, secondhand shops that sell boxes of assorted computer bits, or even your local electrical rubbish tip. You may find heat sinks for microprocessors, but if you're really lucky, then you may even get something nice and beefy, perhaps even using water cooling. This is not a long shot. You would be surprised as to how much electronic junk I have recovered and repurposed. Younger people today are inclined to throw and buy, instead of reusing or repairing. I have a full hi-fi system with amplifier, speakers, tuner, turntable, twin cassette, CD player, and even an MP3 player recorder connected to the AUX jacks, all looking like new. I also have a Canon color laser printer scanner with duplexer for double-sided printing if I had to remove a particularly nasty paper jam. The MP3 player recorder module cost me about $4 from Temu, but the rest didn't cost me a cent. And finally, heat redistribution, calculation, and control techniques form a vast field of study in their own right. There are heat pumps, temperature gradients, junction-to-case thermal resistance, metal conductivity, airflow dynamics, and countless other parameters to explore. Heat sinks are often anodized because a black surface radiates heat more efficiently than a light-colored one, but don't be tempted to paint them. Paint forms a lacquer that adds unwanted thermal insulation. Paper and other stickers also give thermal insulation, so the heatsink is a really bad place to put your property of sticker. Even air pressure, and thus air density, affects convective cooling. This becomes especially critical in aircraft, where cabin air density may be only 65% of sea level conditions and less than 15% outside at 37,000 feet, about 11 kilometers. In the vacuum of space, of course, there's no air at all. And even inside a spacecraft, where the air pressure is normal, there's no gravity, so heated air does not rise. If the subject of heat sinks were an English country mansion set in 110 acres of gardens, maintained by 50 servants, I've merely shown you the doorbell, just enough to get you through the front door and out of trouble. The rest, dear friends, is a lifetime of discovery. Enjoy the journey. So that is about all I want to say about heat sinking. Do have fun, but don't get your fingers burned. Thank you very much for visiting Harry's Homebrew homepages and for reading this far. I hope this information has given you some food for thought. You can email me at harry.lythal@sm0vpo.com or at hotmail@sm0vpo.com, not a typing error, or british.intelligence. Sweden at sm0vpo.com, also not a spelling error. I would prefer you visit my message board if you have any questions. I always appreciate feedback, whether positive or constructive. Original article can be found at sm0vpo.com. Previous articles by Harry SM0VPO.
Silent keys. Please keep these people in your prayers and their families to give them the strength, encouragement, comfort, and peace of mind and heart they need. WL4DX Matthew, WS5J Oscar, WB6I80 Ronald, WB8BHK Herb, N6VFU Rick, VE3PLM Peter, N1MRI Kevin, KK4MBX Francis, KA4Yes Thomas. Disclaimer. The content, opinions, and views expressed in this magazine are those of the authors and contributors and do not necessarily reflect the opinions or views of the publisher, editorial team, or affiliated organizations, or anyone else. All articles, images, and information provided are for informational and entertainment purposes only and should not be considered as professional advice. The publisher, ECR, and its volunteers assume no responsibility for errors or omissions in the content provided. Readers are encouraged to verify all information independently. The use of trademarks, logos, and brand names does not imply endorsement. Reproduction or redistribution of any content in this magazine, in whole or in part, without prior written consent from the publisher, is strictly prohibited. For inquiries or permissions, please contact Vicky K8VKY at Q8VKY@gmail.com.